Okay, let's get started. Good evening, everyone. First of all, thanks for joining this discussion. And myself, Sagar Kesarpu, and here are my colleagues.
Hey, I'm Harikrishna Muriki. I work as a software engineer for a fintech. I'm really excited to be here and present this topic.
Good evening, everyone. I'm Hari Dasri. I'm part of the fintech company, and I'll be working more on this one.
Okay, so before we start, is anyone familiar with quantum computing in this room? Good, 5, 6 hands, as expected. So let's get started with the agenda first. So we'll just go through the basics or the building blocks of quantum computing first, and then we will go through what are qubits, what is entanglement and their properties, and then we'll go through some of the applications that where they use quantum computing, and then we go through the challenges of the quantum hardware, and then some open source tools where you can start your quantum development journey. Okay. So let's begin by addressing the fundamental question: why quantum computing, right? So the world's data and computational demands are growing faster, and classical computers are not able to handle this at the rate which the demand is growing right now. So there are many areas where quantum computing can help us. So there are 3 such areas that I would like to touch upon. One is cryptography, optimization, and machine learning. So basically, when you say classical computing, right? Classical computing is where we use it in our daily life. Like for example, your phone, your laptop. So it always runs on zeros and ones. So that is what classical computing is all about. But so basically, quantum computing is something where it runs based on the basics of quantum mechanics. So the science of how things behave at the tiniest scales, like atoms and electrons, to process to process information in ways the classical computers can only dream of, right? So everything that we run today is on zeros and ones. Like quantum computers are not meant to replace classical computing, but to complement them by solving problems classical computing systems struggle with, right? So let's touch upon cryptography and how can quantum computing help here, right? So there are different algorithms in quantum computing. Like one such algorithm is Shor's algorithm. The Shor's algorithm can break an RSA encryption, which is practically unbreakable with classical computers, right? So what is the current state of our internet today, right? So internet security like SSL, TLS rely on RSA, right, which are hard to crack because factoring large numbers or solving discrete algorithms is still time consuming for classical computers at this day and age, right? So then with quantum computing, there is a threat as well here. So what is the quantum threat towards it? So when you use Shor's algorithm, it can factor large integers in polynomial time, breaking RSA encryption efficiently. So for example, you have a 2048-bit RSA key, which takes a classical computer billions of years to crack. But with quantum computer with enough qubits, you can do it in an hour or less. So what are qubits? I will go on to the next slide and explain you. And what are the implications because of this, right? So it drives the need for post-quantum cryptography, PQS, encryption schemes resilient to quantum attacks. So you need to think about once quantum computer becomes our daily usage. So you should think how can you prevent quantum attacks as well. So once quantum computing comes into picture. So now let's look at the next area, which is called optimization. So quantum algorithms can potentially find optimal solutions for faster in logistics, in finance, and AI hyperparameter tuning. So quantum algorithms like I told, like Shor's is one algorithm, Grover's is one more algorithm which can be used for optimization. So Grover's can potentially accelerate optimal solutions in large search areas. Like you have large amounts of data, that's when Grover's algorithm will come into picture. So there are a few use cases that I would like to touch upon so that you can understand better. So in logistics, you can use it for route optimization for delivery fleets like FedEx or Amazon. In the finance area, you can use it for portfolio optimization, risk modeling, etc. And in AI, you can tune your learning models faster with quantum computing. And there is one company which has already been using it, like D-Waves is the company name. So they use something called quantum annealing system, and it has been tested out, and it is being used for optimizing traffic flow and warehouse operations as of today. Okay, now let's move on to the next area, which is simulation. Molecules and atoms like behave quantum mechanically. Quantum computers can simulate them natively, like aiding to drug discovery and materials design, right? So classical computers struggle with quantum system simulations as of today due to exponential resource requirements. But whereas in quantum computers can natively understand these quantum interactions like electrons, molecules, and atoms. So quantum computing is almost, it's about how electrons, molecules, and atoms work together, right? And then there is one example that I can tell you. So simulating these molecular interactions, right, you can use it for drug discovery. For example, modeling protein folding or enzyme reactions, etc. And you can also use it for designing new materials like superconductors or energy efficient batteries. There are companies which are there in the real world which are already doing that. There is a company called BASF and Roche. They are collaborating with quantum computing startups as of today to simulate chemical compounds faster. So you can create them faster, like the chemical compounds. So, but though the required hardware is limited as of today, and it's very noisy because you need certain requirements to build this quantum hardware, which we'll touch upon in the upcoming slides. But as of today, rapid progress is happening, like open source platforms that are there out there let us experiment and with real quantum systems today. Like there are many companies like IBM, Google, and all. They are providing basic quantum computers where you can go in and you can just register and you can start using them to do your small research or small programs that are out there, right? Okay. Now moving on. So in this slide, I would like to touch upon like how we are moving from classic to quantum, and like what is the difference between classic and quantum computing. Like everyone know, like classical computing is like it basically runs on bits, which is 0 and 1, whereas quantum computer would run on something called qubit. So qubit is the basic building block of quantum computing, which is it can be 0 or 1 or a superposition of both 0 and 1. So what is superposition? We'll go into that much later. But as of now, let's try to understand what are the difference between classical and quantum computing, right? So like the first point I told already, so they use bits, and in quantum we use qubits. And in classical we use something called deterministic. When I say deterministic in classical computing, if you give input A, your result would be input B. So even if you give the same input 100 times or 1000 times, the result would be the same. It would not differ. But it's different with quantum computing. It is all probabilistic, right? So if you keep every time you give an input, the probable result would be different. So that is where it will have different possibilities, or like exponential possibilities for each input that you give. So that is the beauty of quantum computing here. And in classical computing, obviously, you know, today we can just copy data, right? But in quantum computing, you can't copy it as well. That is again because of superposition, which I'll touch upon later. Then you have, in classical computing, you have traditional logics like AND or OR gate. But in quantum computing, you have different gates which are a little bit different, like Hadamard gate or CNOT gate. There is one particular slide completely dedicated to gates, so that my colleague will be explaining. So this is the differences between classical and quantum computing. Now let's move on to qubit. So qubit is the basic building block, right? So now let's unpack this foundation. Let's unpack the foundational building blocks of quantum computing right now. So this qubit can be made from any quantum particle that has two distinct states. For example, a photon of light being polarized either horizontally or vertically, right? Now I want to touch upon the qubits and superposition, right? So unlike classical bits, which are strictly 0 or 1, qubits can be in a superposition. So what do I mean by superposition? A blend of both states at the same time. So let me give you an analogy. Like if you have a coin and if you spin the coin, until it lands, it can be a head or a tail, right? Once you see it, you can determine that it's head, or you can determine that it's tail. But when it is spinning, you don't know whether it's 0 or 1. So that is what is called superposition. It has multiple possibilities before it lands. So, so that is what is called superposition, right? I hope that gets you a better understanding. So this basically, this superposition, this property allows quantum computer to explore multiple solutions simultaneously. So a qubit can have no value at all, or both values, or all possible values at the same time. But it doesn't really matter. So what matters is how it responds to a particular algorithms, like the Shor's or the Grover algorithm that I talked about before. So basically, a qubit can exist in multiple states at once until it resolves. Like I say, when I say resolves, it's head or tail. While in a classical computer, let's say we have 3 bits. So you can when you have 3 bits, you can represent one of the 8 possible combinations that you get out of the 3 bits, right, at any given time. But with 3 qubits in a superposition, a quantum computer can represent all 8 of these combinations simultaneously. So that's the beauty of it, right? And this ability to handle multiple states at once is what lets quantum computers to tackle insanely complex problems way faster than classical computers can imagine of. So superposition is just one piece of the puzzle here. There is another trick up the sleeve that takes things to the next level, which is entanglement. So entanglement is where it starts to feel like science fiction. Okay, so so just let's wait for that. Before we move on to entanglement, let's look at how to visualize the qubit, right? So basically, you can visualize a qubit as a block sphere. Okay, so a block sphere is nothing but a 3D representation of all possible states a single qubit can be in. So unlike classical bits, a qubit can be in any point on the sphere surface, right, representing superposition and phase. So it's not just only binary. Qubits exist on a continuum, so not limited to just 0 or 1, like I told. It can be either 0 or 1. So that is the probability or the phase that we are talking about, right? The block sphere helps us visualize the range of possibilities, making quantum computing more intuitive. So let's understand the axis that is out there, right? So you have z, x, and y. So z represents the classical states, 0 and 1, and y represents the equal superposition. So you can have multiple superpositions within the sphere, right? And then we have y-axis, like which encodes the phase information, which is crucial for quantum interference. So when I say phase, right, you can have one superposition on x and one superposition on y, but the both superpositions might be slightly different by a particular parameter, which you can say that is the phase. Like the phase information will contain that. So that is the key part that differentiates between two superpositions. But why does it matter, right? This visualization is key to understanding how quantum gates manipulate qubits. Operations on qubits are like rotations on the sphere, changing their state and phase continuously. Okay? So now let's move on to entanglement. So yeah, so basically what is entanglement, right? Entanglement is a phenomenon where two or more qubits become linked such that the state of one qubit directly influences the state of the other, even across greater distances. Okay. Now, I know you might be confused with this. Let me give you an example. Like, for example, if qubit A is entangled with qubit B, measuring one immediately determines the state of the other. This correlation is crucial for many quantum protocols, including teleportation, error correction, and certain quantum algorithms. So here is an analogy, like we can again take the same head or tail analogy when you spin the coin, right? So for example, now you have two coins, right? Imagine you got two coins that are entangled when you flip. When you flip one, and if it lands on heads, instantly the other coin also will land on heads, whether it's across the room or whether it's across the galaxy. So that is the beauty of this. Like they are perfectly in sync, like they are sharing some kind of cosmic connection, or like a perfectly coordinated twins, right? So and when one lands on head, the other immediately lands on head, and there is no time delay in this. Right? With no time delay in quantum computing, this linkage lets qubits work together in ways classical bits can't amplify their power to solve problems. So yeah. So when you combine superposition and entanglement, so you get a machine that can juggle tons of possibilities at once and coordinate them perfectly. That's why quantum computers can take on tasks that would leave the best of supercomputers to dust, like cracking codes or simulating molecules. And you can also use entanglement in some applications like quantum teleportation or quantum cryptography. Now let's touch upon quantum teleportation, right? Basically, you're transmitting the same exact state of that particle to another distant qubit, right? And it is basically used in quantum networks to transfer information securely without physically moving particles, basically. So when you are doing teleportation, you would need entanglement plus or classical communication, which enables state reconstruction remotely, basically. So basically, you are moving one state to another state without the use of physically moving particles. And then you have quantum cryptography, like quantum key, which you can say as quantum key distribution. So it's basically uses entanglement again, like they use entangled photons to share encryption keys between two parties, right? Any attempt to intercept or measure the photon disrupts the entanglement, altering users of security bits. So that is where it will be very useful. Like anyone trying to alter or disrupt it, immediately you can find that security breach. So it can really be used for like secure communication, basically. In real world applications, like we are already using it. Like for example, China is using in their satellite communication. They're using it for secure satellite communication. And recently there has also been a breakthrough in India by IIT Delhi students as well as the Defense Research and DRDO, which is a defense wing of India. And they have used the same concept of entangled photons, and they were able to communicate over a distance of 1 kilometer, where they were able to securely communicate between two parties. So those are the uses of entanglement. And now we'll move on to quantum gates, and I will let my colleague Muriki do that.
Hey guys. All right. So think of quantum gates as a musical chords. Okay. So in a classical world, we have zeros and ones, right? You'll get two musical notes one at a time. Whereas in quantum, you can have multiple notes within the same time, so which is creating a more harmony, right? Think of it as a lights where you can on and off along with dimming enhancement to the switch. These quantum gates are used to manipulate the qubits. Okay, so we talked about entanglement. We talked about superposition, right? So how can we do the superposition on the qubit? So we need to apply a Hadamard gate. Okay, let's say we have one qubit. Okay, and we know that we have two states, 0, 1, right? And when you apply the Hadamard gate, you'll probably you end up with 2 power 2, right? So one qubit has one state. Like if you have 3 qubits, you have 2 power 3 states. So imagine these quantum states are part of a block sphere, right? So you're traversing through the sphere, right? So that means 2 power n. If you have 10 qubits, 2 power 10 possibilities of quantum states, so which increases the computing power parallelly. Let's say you have a for loop, right? You sequentially process each one of the loop. You can actually have parallelly compute all the possibilities within the for loop. Okay, so that's a Hadamard gate. Okay, again, we don't want to go into the math equations here. It's introductory. Applying a Hadamard gate onto a qubit creates a superposition. Okay, so 0, 0, 0, 1, and we'll have a. Oops, 1 second. Okay, so we also have a poly X gate which flips the state of the qubit, so 0 to 1, just like a NOR gate in our bit. We also have a phase gates S and T, which actually shifts the phase of the qubits. Imagine you are traversing across the sphere, right? X, Y, and Z axis. Any movement of the qubit, let's say if you want to apply a S gate, you traverse pi by 4 of the phase. At the same time, if you want to apply a T gate, pi by 2. So you actually traverse almost half of the sphere. So these gates again are used to capture the states. You can also traverse back and forth if you have multiple gates. So that's for the single qubit gates, and if you have 2 qubits, you apply a C0 gate, which actually does the entanglement. Okay, so superposition, entanglement, these two are the quantum mechanics principles, right? Applying this onto the qubits will make your system into a quantum state where you can apply all the teleporting, all the quantum mechanics applications. So you can also use the C0 with if and then loops as well. And again, these gates are traversable and operate in parallel. Okay. So moving on to what quantums can do, I think we covered this with Shor's. We have Groover's speed up unstructured search. So I just want to add the unstructured search speeds up from big O of n to root n. Okay, so any spider web of possibilities, even if you are traversing a maze, this quantum computer can actually solve all the results instead of brute force, and gives you a result within root n possibilities. Okay, so that's the same thing that I wanted to add. So this is what we have today. It's actually the quantum computer from IBM. It's put on with the gold plates, runs with filaments, diluted with gold, wiring as well. The reason we do is to capture, to instantiate the actual qubits, because these are very decoherent and very susceptible for the noise. Okay, so IBM is the first actually that has the quantum computer created, and Google has the Sycamore. So how do we actually create the qubits in general? They all live in this different world, right? So there are three types. So we have tiny circuits that can be cooled under 0 temperature. Okay, that's we call as superconducting qubits. Okay, so we can also have trapped ions, which is the electromagnetic fields using the lasers. We can create qubits. Okay, and there is also a photon movement, or where we can instantiate the qubits. So these are all the ways that we can actually instantiate the actual qubits. Again, these are really susceptible to noise and very sensitive. Okay, we need to protect them. The challenge is what to actually because they are actually susceptible, communication between the qubits is essential. Okay, so we have, and we can also we cannot clone the qubits as well, because cloning a normal classical bit is easier, because it has one state. But how can you clone a sphere which has different quantum states, where there is a flip state, there is a phase state, so it's really tough to actually clone the quantum bit. Okay, so we have like several techniques, quantum error correction techniques, which does a proofreading. Okay, one of them is a repetition, right? So let's say I get a text, I kind of whisper what I hear to another person, and the same person whispers to another person. So by the time it reaches the n person, whatever the information that we have given, it totally changes, right? So that's why we actually repeat whatever the information that we want to pass it on to another qubit, and the error correction happens based on the polling. Okay, and we also have a stabilizer codes where we kind of acts as a guardrails with multiple. It has some rules that goes into it. Okay, and it goes through the phase bit and bit flip corrections. Okay, And we also, this is the surface code is actually the most popular and widely used. It puts all the qubits in a 2D plane, okay, and the information, it actually multiplies the qubits and then picks up the right one. So it compares. It's like think of it as a chessboard where you put all the qubits in one, and you put all the redundant qubits next to each other, and then corrects whenever there is a flip. Okay. So those are some of the techniques. So we have several tools within the open source, right? We have a wide range of frameworks, simulators, and as well as community resources, where we can actually access and we can actually simulate the quantum state in the classical computer. Okay, so we'll go into we'll instantiate some of the qubits in the classical machine. Okay, and we'll apply some of the Hadamard gates, and we'll put a qubit in a superposition, and then we'll entangle them. Okay, and see what's the possibility of getting getting the probability of getting the state of the quantum. Again, when we measure the state of the quantum bit, right, it falls down to that measurement. So we don't want to measure that, but just for the sake of the experiment, we'll measure that in a minute. Okay. Yeah. So these are some of the open source tools that we have with IBM, with Qiskit, Cirq, with Google, Pennylane, CUDA. It all comes across frameworks and simulators, and we also have an awesome quantum software foundation, right, where you can pick up any open source projects and contribute to it. Okay. So let me try and show you. Oops. Okay. All right. Okay, so this is Qiskit. This is actually the libraries provided by the IBM. So it's all open source tools. Okay, so quickly I picked up the quantum circuit. This is something that we have seen, right? The quantum circuit is where we instantiate the qubits. Okay, using the electromagnetic circuits, and we have a simulator where we kind of simulate the quantum environment within our system. Okay, and we use some of the plotting to see what's the results are. Okay, so this is I just instantiated a couple of qubits, 2 qubits and 2 normal logical gates. Okay, we apply the Hadamard gate for qubit 0. Okay, and then for the C0 to entangle just one of the qubit. So qubit 0 is entangled with qubit 1. Any change of state in 0 will be applied to the qubit 1. Okay, and then we measure the qubits. Remember, when we measure the qubits, it goes back to the same stage. So let me run and see this. Okay, as you can see, we have 2 qubits, right, 0 and 1. So it's almost we ran like 1,000 times. Okay, so these are the 1,000 possibilities. We imagine we flip the coin like 1,000 times, and we have like almost close to 50% of the states in 0 and 50% of state in 1. Okay, because they both are entangled. And again, we heard that it is probabilistic. Okay, not deterministic. So every time you run, it's non-deterministic. Okay, so this is close to 50% still. So that's one from the IBM. So we have a similar one from the Google. Okay, so this is similar. We instantiate the qubit, apply the gates, and see the results. Very straightforward. Yeah, almost close to 500. Maybe try it again. Yeah, pretty close. Again, yeah, you can actually instantiate this. This is a quantum environment I've created from within the normal computer. Yeah, it's pretty straightforward. I would encourage you guys to explore some of the repositories and go through that. Let me go back to the slides and we will go back to this.
Right. I think you got some information about in the demo. So we'll talk more about like how we can start that, like how we can have this hands-on, like how we can do that. So there are a lot of options which we have. So in that IBM Quantum, they have that lab, and we can go and sign up and get more information on that, and also we can play around. They have so that we can directly interact with the whole quantum platforms. That's one of the way. And of course, we have the open source communities where we have this Slacks and GitHub, and also we have Cirq dev developer groups where we can go and explore, and a lot of GitHub repositories are also there. So we have the exploring this Microsoft Quantum katas, and also contributing to the docs and visualization codes, everything are also available. So that's the first initial way to start about how to go in and get into the platform and do some more hands-on on it. Coming to the next is, look, what's next? What are the future trends? What's happening in these quantum computing? So it's rapidly evolving. So some of the things which they're talking about is like more on hybrid quantum and classic workflows. In the previous slides, we already talked about like what is quantum, what is the classic workflows and everything. Now, how we can integrate that, how we can hybrid that. Ideally, as you were seeing, the quantum computing can be used for specific tasks like optimization, simulations, or entanglement-based operations. Whereas the classical computing, where we can use more on the orchestration, pre-processing or processing. So now, just imagine it's like more like a teamwork. Instead of like quantum chips, ideally quantum chips doesn't replace the classical computers. Instead, what we are trying to do is they handle the tricky things, and then they are optimizing the molecule structures and send the results back to the computer. So that's where we will be using our classical computer to finish the job. So whatever we are seeing, the zeros and ones, whatever we are talking about, but ideally in a human way language, when we talk about, it should be displayed in a proper display. That's where we will be using the classical way, whereas in the back end, all the tricky solutions will be done by the quantum. So we are trying to integrate the quantum-based and the classical workflows are getting integrated, and there's a lot of research happening on the both of them. The other second thing is definitely the quantum as a cloud service, which we were talking about before. Like a lot of cloud providers, also they have their, so they're providing the service, which we talked about IBM. There is Amazon. They also have their own service. Azure has their own, Microsoft Azure has their own service. So different ways, because it's like an on-demand thing, which we can go and use instead. Like we don't need to set up the whole platform by ourselves. Instead, we can use the on-demand, and you can try to use as much as possible. That's the other thing. And other part which I want to talk is like domain-specific quantum libraries. Basically, it's if all these domain-specific things is like, we don't need to rebuild anything, or we don't need to, start everything by ourselves from scratch. So it's all, there are a lot of libraries which are available. We can directly use them, and also, it's more like instead of reinventing the whole wheel, you can use the already available quantum tools, which are again built by the experts and domain experts as well as the developers. Examples are like, if you are into the financial sector, there is a Qiskit finance to optimize the portfolios and everything, and we don't need to design the whole circuits by ourselves. So like that, there are a lot of libraries depending on what domain you are. You can have that libraries can be used. Other thing I want to bring it is like quantum education goes. currently there is a lot of universities, they are coming up with the degrees in both in bachelor's and master's, more on the quantum computing. And also when it comes to like ours who are already working on it, there is a lot of certifications. And IBM has their own certification, it's a quantum developer certification, which we all can also have a lot of material, everything, which we can play around, we can read and as well as play around with that platform which they are giving. Then it also gives more practical and also the theoretical knowledge about the certifications. The other one is like the quantum app stores and SDKs. Like, we have, there's a lot of example like mobiles, we are using the iOS, there is a lot of apps coming up. Now, they are also working on creating the more tools in the apps so that, ideally we can use the tool optimizers and everything to download into our mobile devices and also use install this one in the libraries and everything and try to do whatever the practical things which we want to do. Other part which also we want to see is like, again, these are like, we are at the early stages of the quantums. The tools, there are a lot of tools, platforms are there are a lot of opportunities which we can explore and, we can try to understand more on the quantum and explore more on them. Coming to the summary, I just want to wrap it like what we understood from here, like we are trying to give the basic, the beginner's thing guide on how the computation models, what is the quantum, the computation model, and what is qubits. I think my colleagues already explained more about what is the qubits and everything. Other thing is like, which I want to bring is open source is also having, this lowering the barrier to entry basically. So that's where we have a lot of resources which are available, which will be useful more for us to go ahead and think. And there's also like, explore the real quantum devices today, which are some of them are free. Yeah, that's all. Thank you very much for your time. If you have anything, let us know.
Any questions? Thank you.
I have, I think, simple question. In classical system, we have persistent memory, volatile memory, and processing core. So qubit is fragile, entanglement is fragile. So qubit may exist in current state of the art, if I correct around, maybe several seconds. It's the more. So if you are talking about quantum AI or real life problem, we need to process a lot of data. We need to have persistent memory. And currently qubit, it looks like it's something like we have only something like processing core, because with quantum gates, it's only processing core, nothing more. So, and currently I don't see what is the persistent memory, even volatile memory in the quantum world. So what's vision when we will have in 10 years, 20 years, when we will have a real memory, because it will be better to have something like maybe, because it's a lot of talk about photonic processors. And in the best case for quantum computing, we need to have something like photonic memory. So what's, we can, otherwise we cannot talk about quantum AI.
Yeah, so maybe I can take this. Yeah. So yeah, I think we are still evolving in there. If you see the actual quantum computer, it's almost about half of this room, right? So we have several types of storages like block and ephemeral storage as well. And as you can see, some of them, the gold plates and even the quantum state, there are several ways to instantiate the quantums. Again, it's based on the evolution, right? We might plug and play several type of storages based on the entanglement, and let's say, even the computers, if I remember, has more space earlier, right? We had several types of storages, right? But things keep changing there. I believe it's really hard to kind of put in what exactly what type of storage that it we can tie to this particular quantum mechanics, but hopefully things might move sooner on the hardware space rather than the processing space.
The picture that you shared for something like, is it, I don't know, is it IBM stuff, or it's something like superconducting qubits.
Right.
And if you would like to connect with existing persistent memory,
Right.
it's not superconducting.
Right. Yeah. Yeah. Superconductors. Yeah. Yeah.
Thank you. I simply
Thank you.
decided to share some thoughts.
Thank you.
Thanks for your thought.
Yeah, I think there's a lot to understand, to be honest. So, the basic thing that I could understand from coming from app dev, right? You talked about RSA key, right? It has a bit length and all, right? So, with complex, it does those. Classical one, it does those with a 256 bit. What happens when you cross over? What quantum brings in when you basically go beyond 256 bit memory and all?
Yeah. Yeah. Currently, it's 2 power 256, right? It's gonna process as quickly. Again, we have. I think Sagar talked about quantum, post-quantum cryptography, and we can add more hashing into that. We can add several code-based techniques to incorporate that. Again, we might leverage quantum's help there. But yeah, that's a good question. I was heard about RISC team raising these questions about decrypting the keys, because it's a matter of time where you can access all the personal records in a moment.
Yeah.
Thanks.
So I know this is too much of information, and you might have understood what superposition and entanglement is. But if you really want to understand superposition and entanglement, I would suggest you to watch a web series on Apple TV called Dark Matter, which will explain of how quantum computing works. So superposition and entanglement you will clearly understand in Dark Matter, the web series that's there on Apple TV right now. Yeah. Any other questions?
Hi, really fascinating stuff. I think we're all still absorbing. That's why we're stunned silence here, at least for me. So 2 questions. One is, I think you've already answered the size of that thing that looks like a chandelier. That's actually the quantum computer. That's half the size of this room.
Yeah.
So we're basically in the ENIAC stage of quantum, right?
Yeah.
But how far along? When do you think this will actually shrink to the size of a mini computer or a car?
Yeah, I think last month I've seen some of the articles. Even we were actually researching on this topic. I think it's about 5 to 10 years.
Oh, so 10 years.
Is what Google says.
Okay.
I think they I'm not sure if somebody covers with Sycamores, Google. They actually were able to factor some of the some of the calculation within like 200 seconds rather than 15 years, right? Again, even our systems were like almost half of the room in 1960s or 50s, right? So it evolved. Thinking the same thing, this is one of the way to actually instantiate the qubits. There's also trapped ions. There's also photonic chips with. If let's say if we find another way of spinning of electrons, right? It's all quantum physics. Everybody is evolving. So maybe the size can reduce. Again, this has to be within very less temperature. It has to be like cold.
Yeah, it should be at minus 425 degrees centigrade, and it should be completely noiseless. Even if the slightest of the disturbance could disrupt it completely. So building this itself is a very big task.
Expensive.
So hopefully in the coming years.
So one other question, just to follow up. So how many qubits does this chandelier actually make?
Yeah, I think it's 30 qubits. That's about
30 qubits for this.
Yeah, 30 qubits.
And 30 qubits is a lot.
There's a lot.
Yeah, and so if we have a 300 qubit, we can actually define all the states within our universe.
So that's basically answer the question of life, the universe, and everything.
Yeah.
We already know the answer. We can get the question. Okay.
Some guys don't believe at all in quantum computing.
Okay. Thank you.
What do you guys think about like alternative physics-based computing technologies like photonic neuromorphic computing, which does not require a dilution fridge to like cool down a chip to -7 millikelvin to solve non-deterministic problems in polynomial time?
Yeah, I'm not sure. I think this is the next evolution after 5 to 10 years.
Yeah, because there are some open source libraries that like for photonic spiking neural networks that are inspired by the neurons in our brains. So is there something you guys think about? And there are already like systems, photonics based systems that have like 200,000 spins to simulate different problems like node cut problem for calculations.
We don't have any idea of that alternate physics that you're talking about. To digest quantum mechanics itself is a huge task for us because we are basically programmers. So even to think at this angle was very difficult for us.
Yeah, I'm sure it is. Like you guys are great. Yeah.
Yeah. So
thanks for the presentation.
Yeah, we were just exploring the open source tools that are out there,
and also, yeah, we should remember that this does not replace our classical computers, right? We just, just like our passenger planes versus the rocket, right? It each has a different purpose. Only when you require a high-speed calculation, we'll use the quantums, not for all. In fact, it actually reduces, it takes more time if you process some of the things within the quantum computer.
Yeah,
so
definitely much more suited for like NP hard problems.
Yeah, exactly. Yeah. And thank you for your question, and thank you guys.
Thanks
I
everyone.
hope you like it.
Oh,
yeah. Sorry. Go ahead. I think we still have time. Oh yeah.
Oh, okay. Thank you.
I realized I didn't really understand what you were doing when you showed us the Qiskit terminal.
Mm-hmm.
What were you, like, what was that? And can you give an example of how you, like, what are you doing in the open source space? If you're just messing around in Qiskit as an open source contributor, like, what are the kinds of things you're testing out and exploring?
Yeah, definitely, yeah. How would I? Thank you for your questions. Actually, this really helps us. Where is it, man? 1 second, okay? Let me.
Yeah, no, it's up. No.
All right, yeah. Okay, so what we are trying to do is we are instantiating 2 qubits, okay, and 2 classical bits in here, line 10.
What is that like? What are you trying to answer?
Okay. No. Okay. So here, right? So what I'm trying to do is I'm trying to instantiate 2 qubits, okay, and then I wanted to put that qubit in a superposition, and then entangle it, okay.
So you're just like turning it.
What is that?
You're essentially just turning it.
So what you're getting out of it is all the possible outcomes that you can think of by entangling these 2 qubits. So that's what we are trying. So like I gave you the analogy of a spinning coin, right? Before it turns heads or tails, can you measure like what are the superpositions that are there when it's rotating still? We don't know, right? So that is what we are quantifying through this algorithm. So like he showed you the bar graphs, right? The 500 or 600 possibilities that we have. So that is what we are achieving. So the number of possibilities that we can get.
So you're literally just demonstrating like what does the quantum classical interface look like?
Exactly. Yeah. So this is the quantum environment that I think this is what I had it, the quantum-env Hari. So you can actually instantiate, create your quantum environment. I don't know how it does. It's a Python libraries. So you can instantiate and you can put, import some of the libraries, right? So with 2 qubits, 0 and 1, okay. So with what I did is applied a Hadamard gate on qubit 0, okay, and put that in a superposition, okay. So for first qubit 0, qubit 1, both have state 0, okay. When I put that in a superposition, it has one state, either 0, 1 or both, right? And then I added a C0, which is the entangle. So changing a state of qubit 0 will change it on the 1, okay. So then we are capturing the results. That's it. That's all we are doing. So this one, what we are doing, line number 12 is actually entangling control bit, qubit bit 0, and we are applying the results on the target bit, qubit bit as 1. Now running this showed us that the entanglement works, right? So I did not do anything on the qubit 1, right? I only did it on qubit 0 and ran like 100 heads and tails, 1000 heads and tails, and this is what the result was. So this is the qubit 0 and this is a state of 1. So again, teleportation, if, let's say there is another qubit in another galaxy, I want to mimic that. So you apply some gates, don't think too much, to apply some gates in such a way that it will behave same. That's it.
So when you see a result like this, all this is telling you is like they are identical.
Yeah. Exactly.
Yeah.
Exactly. I hope that's how the quantum is. So. Yeah, I think.
So they're entangled, but the results are identical between the two.
Yeah. Almost 50% of probability.
Is that because of errors in the quantum
Yeah,
computer?
that's correct. Exactly. That errors because. Yeah, exactly. Yeah.
And now that we're already halfway in this, so if you remove the entanglement, would you get like 4 different equally distributed states?
No, if you remove the entangled,
You have to apply the Hadamard to the 1.
yeah,
And then run the simulation.
exactly.
You get 4 different states.
Exactly. Yeah, that's correct.
Thank you.
Thank you. Thanks for your questions. Yeah, it's a simulator. Yes. Exactly. Yeah. I mean, it does simulate the errors, but it still shows some errors. But I don't know. Yeah.